Hello, dear students. This is your Professor Lázaro Pino. Today we have chemical mixtures, solutions, and other mixtures. What is a solution? A solution in chemistry is a homogeneous mixture of two or more substances in relative amounts that can be changing continuously up to what is called the limit of solubility. Likes dissolve likes. Then what does it mean? First of all, in a solution, there is no chemical reaction. It's only a physical change where two substances mix together to make a solution that is made by a solvent and a solute. We have different kinds of solutions: gas in a gas in a liquid, gas in a solid, liquid in a liquid, solid in a liquid, or solid in a gas, as you can see in this table. Based on whether the solution is water or not, solutions are of two types: aqueous solutions, where water is the solvent, and non-aqueous solutions, where the solvent is different from water. Example, ether, benzene, carbon tetrachloride, etc. Thus, definition of solubility is very important when we are talking about solution. Solubility is the concentration of solute in a saturated solution. For example, the maximum amount of table salt which can dissolve in 100 grams of water is 36 grams at 20 Celsius degrees. This is the solubility of table salt at this temperature. Remember, always we have to set the temperature. Here you can see in this graph different curves corresponding to different substances. All of them are salts, uh, ionic salts. As you can see, in general, as the temperature raises, the solubility also raises. They are directly proportional. This is what happens generally in solids and when a liquid is dissolved in another liquid. Concentration of a solution is the ratio of the solute to the solvent. Concentrating means that there is a relatively large amount of solute in a solvent. Dilute means that there is a small amount of solute in comparison with the amount of solvent. Then an unsaturated solution admits more solute to be dissolved. The saturated solution does not accept more solute to dissolve. Then when you add crystals, they remain in the bottom and they don't dissolve more. And a supersaturated solution is that one that contains more solute that is possible for an amount of solvent at certain temperature. Those solutions are unstable, and just if you add an extra crystal, precipitates, and you can see it in the bottom, a lot of precipitate. The intermolecular forces are very important during the process of the solution. because there are forces that may or help, and some of the forces that are opposite to the formation of the solution. Here we have different examples of intermolecular forces: dispersion, dipole-dipole, hydrogen bonds, and ion dipole. For the solvent and solute to mix, you must overcome, number one, all the solutes forces. When I'm talking about this, I'm talking about the forces that attract one particle of solute to another one. And also you have to overcome some of the solvent-solvent attracted forces. Both processes are endothermic. At least some of the energy to do this come from making new solute-solvent attractions, which is an exothermic process. Here we have the interaction solvent-solvent and the interaction solute-solute. We have to break these interactions in order to get new interactions between the solvent and the solute in order to get the solution. If the attraction between solvent-solute are higher than the interaction solvent-solvent or solute-solute, then we can say that the solution can be formed. If the solvent-solute interactions are equal to the solvent-solvent and solute-solute interactions, also the solution can be formed. But if the solvent-solute interactions are smaller than the solvent-solvent or solute-solute interactions, then the solution may or may not form, depending on the relative disparity. Always that we make a solution, we are supposed to lower the Gibbs free energy. And it happens almost always because the entropy of the solution is higher than the entropy of the solvent alone and the solute alone. As the entropy is subtracting the enthalpy of formation, then this number lower and the energy, the free energy also lower. Here we can see the process. First, we have the enthalpy of the solvent, that is when we separate the solvent particles to make room to the solute to go into these particles. But also, this process is endothermic. It means that that the process absorbs energy in this step. Also, separating solute particles is an endothermic process. But if you go to the process of mixing solute and solvent particles, this process is exothermic. And the process generally, if it is higher than the addition of the two first steps, the resultant enthalpy, the enthalpy of the solution will be also negative, and the process will be exothermic because this energy is released to the environment. Here, there is an explanation of this process. If the resulting energy of the solution is endothermic, then the process absorbs energy during the dissolution. Heats of hydration happens when aqueous solution of an ionic compound, we add energy to overcome the attraction between water molecules and the energy released in forming attraction between the water molecules and the ions. And all this is combined into a term that is called heat of hydration. Then, the attractive forces between the ions is what we call enthalpy of solution. And it is equal and opposite to the energy of the lattice. That is the energy that remains joined together the different particles in the solid lattice. In other hand, we have the attractive forces in water that are the hydrogen bonds. We need to break these forces in order to get new forces of attraction between the ion and the water molecule. These attractions are ion dipole. The ion is the cation or the anion of the ionic compound, and the dipoles are the water molecules. The enthalpy of hydration is equal to the heat released when 1 mole of the gaseous ions dissolve in water. So the enthalpy of hydration is equal to the enthalpy of the solvent plus the enthalpy of the mixture. Here we can see the process of hydration. In the process of hydration, we have solvation. That are the interaction between the solvent and the solute. And the hydration is the solvation by water. What is the enthalpy of hydration? The enthalpy of hydration of an ion is the amount of heat released when a mole of the ion dissolves in a large amount of water, forming an infinite dilute solution in the process. Here we have a representation. We have the ion in the gas state and M water molecules that will produce the aqueous ion. The second step is to disperse the ions or hydrated ions into the solvent medium, which has a dielectric constant different from vacuum. The amount of energy is called energy of dispersion, enthalpy of dispersion. Therefore, the enthalpy of hydration is equal to the enthalpy of dispersion plus the enthalpy of the ligand. This idea is brought up just to point out that the formation of aqua complex ions is part of the hydration process, even though the two energies are not separable. When a stronger coordination is made between the ions, you can use other ligands to replace the water molecules, and then you get another complex ion in the solution. In this case, ammonia replaced the water as ligand in this complex cation, and now we get a new one, and the water is replaced. The expanded solute uh, is become from the separation of the solid particles. This is step number one. The solvent separates its particle and we get the expanded solvent. So that we can get the formation of the solution when these particles of the solute takes the rooms into the solvent molecule. Let's see the energy changes in solutions. Why do some ionic substances dissolve in water while others are insoluble? Well, the answer is here. If there is enough energy to separate the ions in the lattice, the substance will be soluble. Here you can see how the particles of the solid are between the solvent molecule. The lattice enthalpy, that is this one, is the enthalpy change when one mole of a solid is formed from the separate ions. This is always an exothermic process. Then the enthalpy of the lattice is always negative. The energy to break up a lattice is a negative magnitude. That is the one that I represent here. The sign negative means that the process is exothermic. In other words, that the energy is released. Which will give more negative enthalpy of the lattice? A small ionic charge, large ionic charge, or a small ionic radius, or large ionic radius? The answer is large ionic charge and a small ionic radius will produce a more negative energy of the lattice. So, in other words, release more energy. Where does the energy come from to break up the lattice? From hydration. Enthalpy of hydration, as I told you before, is the enthalpy change when a solution of ions made from one mole of gaseous ions. Is hydration exothermic or endothermic? Exothermic, because bonds are made. Example of hydration. Here we have the sodium cation that is mixed with water to make a cation in aqueous solution. The enthalpy of hydration is this number that you can see here. An ionic compound contains cations and anions. The total enthalpy of hydration is equal to the enthalpy of hydration of the cation plus the enthalpy of the hydration of the anion. When sodium chloride is dissolved, then the enthalpy of hydration is equal to the enthalpy of hydration of the sodium plus the enthalpy of hydration of the chloride ion, which will give more negative enthalpy of hydration. Let's see. Oh, large ionic charge and a small ionic radius. Remember always this, the larger is the charge, and the smallest the radius, the ionic radius, the enthalpy of hydration will be more negative. And remember, that's good for the formation of the solution. Water is not the only solvent. Then the enthalpy of solvation of the solvent can be represented this way. The enthalpy change of a solution, this is the enthalpy change when 1 mole of solute dissolved to form an infinitely dilute solution. The enthalpy of the solution is the enthalpy of hydration of a cation plus the enthalpy of hydration of the anion minus the enthalpy of the lattice. That's why we said that the more negative it is, the more exothermic is the enthalpy of the lattice, will help more to make the possible the solution because we'll lower the enthalpy of the solution. Remember, the lower the enthalpy the solution, the more probably it will be possible that the substance will dissolve. Never forget this. What decides solubility? Energy is put into separate the ions in the lattice. The energy is released by hydration of the ions, and if more energy is released than used up, then the enthalpy of the solution will be negative, and the solute is more likely to dissolve. Here we have the cycle for the solution. In one hand, we have the ionic lattice plus the solvent to make the solution. In this case, is associated to the enthalpy of the solution. But in other hands, we have the enthalpy of the lattice that produce the gaseous ions. And in the other hand, we have the hydration of the cation and the hydration of the anion that makes possible that the enthalpy of the solution will be equal to the enthalpy of hydration of the cation plus the enthalpy of hydration of the anion minus the enthalpy of the lattice as we have seen before. Here we see that the enthalpy of the solute plus the solvent to make gaseous ions is endothermic. But the enthalpy of hydration is exothermic. So the resulting enthalpy of the solution is also negative. So the process is exothermic. But if the enthalpy of the solution is positive, then the process is endothermic or exothermic? Of course, endothermic. Solubility. The more negative the value of the enthalpy of the solution, the more likely the solute is dissolved. If the enthalpy of the solution is very large and positive, the solute will not dissolve. If the enthalpy of the solution is small and positive, the solute may dissolve if there is sufficient increase in entropy. Here we have the solution equilibrium. When you begin dissolving the cations and the anions in the lattice into the water, you can see how the process goes into the direction of dissolving. But when the solution becomes more concentrated, then begin an inverse process of recrystallization. Some ions in solutions will go into the solid state and precipitate. Then dissolution and precipitation are processes that at certain time of the process are at equilibrium. So that maybe you think that the process of dissolution and deposition or recrystallization are over, but at the level of microscopic level, the both processes continues equal with the same rate, but in opposite direction. And that's what we call dynamic equilibrium. The maximum amount of solute can be dissolved that can be dissolved in a solvent at a specific temperature is what we call solubility. As you can see in solids, the higher the temperature, the higher the solubility. And at every temperature, we have certain solubility. In gases, and is the opposite. When the temperature raises, the solubility of the gas lowers. What happens if we change the pressure? Well, the solubility of solids and liquids don't depend on the change of the pressure. The solubility remains constant even though you increase the pressure. It is the opposite for the gases. If you increase the pressure, the solubility of the gas increases. That's why when you open a bottle of soda, gas is released because as the pressure is lower than the one that when the bottle was closed, a lot of gas is not dissolved anymore and is released to the environment. How can you make solvent hold more solid than it is able to? Well, if you begin from an unsaturated solution and you begin adding more solute and more solute, you can get a saturated solution. If you get this, no more solute can be dissolved. But if you increase the temperature, you can see that the solution becomes unsaturated because at that temperature will accept more solute. So if you cool very slowly this supersaturated solution, you will see that no precipitate is produced. And at this temperature that was supposed to get to support only 90 grams, 91 grams, well, in this case, have in solution 100 grams. Then this solution is called supersaturated because has more solute than is possible be dissolved at that temperature. These solutions are very unstable and just adding a crystal or just touching the walls of the beaker, a lot of particles precipitate and you get the solid in excess again, and only in solution will be the amount that is possible to be dissolved at that temperature. This process is used to recrystallize certain substances, and in that way you can purify them. There are different types of expressing concentration. Molarity is the amount of solute in mole per liter of solution. Molality is the amount of solute in mole, but in kilogram of mass solvent. Mole fraction X is the amount of solute in 1 mole divided by the total amount of moles of solute and solvent. The mole percent is the amount of solute in mole divided by the total amount of solute and solvent in mole, multiplied by 100, of course. Parts by mass. Mass of a solute divided by the mass of a solution, multiplied by a factor, can produce, if it is 100, the factor is percentage. But if it is 10 to the 6, is parts per million. And if it is 10 to the 9, it is part per billion. ppm and ppb. The parts by volumes can be also expressed, but instead of using mass, you use volume of solute and volume of solution, using the same factors that we use here. Let's see, the molarity of a solution formed by 6.75 grams of sodium chloride dissolved in water to make a solution with total volume of 452 milliliters of solution. In this case, you have to convert milliliter into liter because the concept is liters of solution. Well, you know that you have 100 milliliters in 1 liter. So you cancel milliliter with milliliter and you have the volume in liter. And you have to convert the grams into mole. You know that 1 mole of sodium chloride, in this case, is 58.4 grams of sodium chloride. So you cancel out grams and grams, and you get mole per liter. The solution has a concentration of 0.256 mole per liter, or molar. That is molarity. Solution concentration in molality. Remember, you use kilogram of solvent. Here you have an example that you can stop the video at any time and you can study. How can you calculate the molality? Remember, there are moles of solute per kilogram of solution. And here you have ppm and ppb. These are two other important forms of expressing concentration. In general, concentration is the relationship between amount of solute per amount of solution. The colligative properties are those that depend on the number of solute particles present. It doesn't matter what is the type of solute that you have. They are the vapor pressure lowering, the boiling point elevation, the melting point depression, and the osmotic pressure. The Rolle's law is used in the vapor pressure lowering. The vapor pressure is in this case P1. Uh, and this is the pressure of the solvent that is directly proportional to the mole fraction. That is, remember the mole fraction is the moles of the solute per the moles of solution. Then the expression of the Rolle's law is P1 is equal to X1 times the partial pressure. The partial pressure of the vapor of the pure solvent. Then, if the more of solids, if you add more solute, what will happen? That the the fraction will decrease and the partial and the vapor pressure will also lower. That's why we can use this law to study the behavior of adding solute to solvent. In this case, we can see that when we have a very strong solute solvent interactions, the vapor pressure is not a straight line, is this way. But if these interactions are very weak, then the vapor pressure has this form. These are deviations from Rolle's law. The boiling point elevation and the freezing point depression. Non-volatile solute-solvent interaction also cause solutions to have higher boiling points and lower the freezing points than the pure substance. We can say, for example, that we can study the increase of the boiling point if we add a solute to the solution, because the enthalpy will be directly proportional to the R constant times the temperature divided the enthalpy of vaporizations times um, a number that is called molality, that is B, and I, that is the Van Hout factor. Kf is what we call cryoscopic constant. This constant can be obtained, and also the Van Hout factor is a constant. You can obtain this number, so you can say that the freezing point lowering or depression can be calculated knowing what we call the molality of the solution. Then, osmosis. Osmosis is the flow of a solvent of a solution from low concentration to high concentration when you have a semi-permeable membrane. The liquid or the solvent will go in the direction of where there is a higher concentration. So you can observe something like this in a beaker, that this lever raises because there is more particles here until you get same concentrations in both sides of the semipermeable membrane. The osmotic pressure is the pressure needed to keep the osmotic flow from taking place. The osmotic pressure is represented by the letter pi and is directly proportional to the molality of the solute particles. This is the R constant and this is the temperature. Here we have a representation of the red cells. When the red cells are in blood, in the plasma, the concentration of the plasma is similar to the concentration of the red cells. So no liquid goes in or goes out, or if water goes in and goes out, is at the same rate. And the red cells are normal, as you can see in this image. In the middle, what is going on? Oh, there is a higher concentration outside. So the osmotic pressure makes the water goes from the red cells out to the solution. And what happened with the red cells? They shrivel, they shrink. So this process is called shrinkage. If, in other hands, the concentration outside in the blood is lower than the concentration inside of the red cell, the liquid goes in and the red cells increase the volume. That's what we call swollen. It can produce that the red cells can be broken and produce a process that is called hemolysis. Both processes, the shrinkage and the hemolysis, are bad for the person that is suffering it. So it's very important to get under control the osmotic pressure of the solution. And how we get that? Well, taking into account the concentration of the ions in the solution of blood. Blood is made, as you know, by a solid and plasma that is a liquid part. Well, we have mixtures, could be uh, solutions, could be suspensions, or could be colloidal dispersions. It depends on the size of the particles, as you can see in this graph. When we have a size between 1 nanometer that correspond to the solutions, and we have and 0.5 micrometer, that is the size of the particles in the suspensions, we get what we call a colloidal solution. Colloids are heterogeneous that do not separate on standing. Particles can coagulate, cannot pass through, the particles cannot go through a semipermeable membrane. They suffer of hydrophilic interactions. So this hydrophilic interaction made possible to stabilize the attractions between the solvent molecules. And also, we have hydrophobic interaction that is stabilized by the charge of the particles that are in suspension. As they have the same charge, the same size, what happened? They repel. They repel, and it makes possible that the particles, the colloidal particles, are all over the substance without coagulate. These colloidal systems suffer of Tyndall effect and Brownian motion. Here we can see what we call Brownian motion. Particles move erratic, in an erratic way. And the Tyndall effect is when you have a solution and a red light goes through it, you can observe as, as a point where the light incides. But in the case of a rate of light that go through a colloidal system, what happened? That what you get is a very large space reflecting the red light. Why? Because the particles of the size of the particles of the colloidal particles scatter the light, and that's why you get a diffuse rate of light in, in when emerge from the solution the light. This is what we call Tyndall effect. Well, that's all. I hope you can understand. If you have any doubt, you can uh, send me messages and I will answer as soon as possible.